So, hello everyone, welcome back to the channel. So, today we are going to solve this question called interesting sequence on the code forces. So, here we go. So, you are given two integers n and x, and this is the equality that they hold, that you start doing AND operations on the numbers starting from n and going forward, n and n plus 1 and n plus 2, so on up to m, and this expression should give you x. So you are given n and x, and you have to find what is this m, means what is the number m, so that n and n plus 1 so on up to m is x. So we have to find minimum m, such minimum m. So that is basically the question. So let us take a look at this sample test cases. 10 8 10 10. So 10 8 and 10 10. So binary representation of 10 is 1010, and binary representation of 8 is 1000. So so let us see. uh, Binary representation of 11 is 1011 and 12 is 1100, and if we add these three numbers, uh, we will get 8. So let us check it. Yes, we are going to get 8. So we have to find this number m, minimum such m. So in this case it will be 12. Okay, so for in this case, trivially, if n is equal to x, answer is going to be n, because it is said that m is greater than or equal to n, or equal to n means m can be n as well. So when n is equal to x, our answer is directly going to be n. So we can break this question in some cases, some important cases. So what we will do is that, first case, trivial case, just now we saw that if n is equal to x, then our answer will be nothing but n. Okay, so but if x is greater than n, our answer is going to be -1. Okay, so because there won't be any m such that the given, what you can say, the given equation holds, because in any number a and b, where and is bitwise operation, uh, so and is bitwise operation, so a and b is going to be less than or equal to minimum of a and b. Okay, so it is never going to exceed the minimum of these two numbers, but here it is exceeding n. Okay, so it won't be possible. So third case is that if x is 0, suppose. Okay, if x is 0, and this is the edge case. Okay, this is definitely an edge case. So what we can say is that, so if x is 0, suppose my any number, suppose let's take 8, n is 8, this is in binary, and my x is 0. So when will I get 0? Okay, when will I get 0? So I will get 0 when my m becomes 16. Okay, because all these numbers will have their most significant bit as 1 and at position 0 1 2 3. But when we come at 16, the this bit at the third position 0 1 2 3 becomes 0, and finally our answer is going to be 0. So whenever x is 0, we have to calculate the power of 2, power of 2, power of 2 something, suppose power of 2, which is greater than the given number. Okay, so greater than the given number. Okay, so this is going to be our answer. And yes, so these are some cases or base cases, and finally we move to general cases. So suppose let us consider solving this problem by considering bitwise entries in each number. So suppose some ith entry, you can say ith entry in the binary representation of n is 0, and in x it is 1. So will it be possible to make it 1 by doing AND operation with 0? No. So in this case, answer is not possible. Answer is going to be -1. Okay. So that is the thing. And next, suppose n is 0 and x is 0 at the ith index. So this is the trivial case. Okay. We don't care what the bits in n plus 1, n plus 2, and n plus 3, whatever it is, what the bits at ith index are, because 0 and 0 is 0, and 0 and 1 is also 0. So this specific case doesn't tell anything about the answer. So suppose at ith index n's bit is 1 and the corresponding bit at that position in x is 0. Okay, and the fourth case is at the index I. Suppose I is any index. So fourth case is that bit is 1, and here also it is 1. So these two are going to be the determining aspects of our solution. So what I can see is that, suppose my numbers are, suppose any random number 1 1 0 1 1 0 1 1 0. Okay, and second number, let it be 1 1 0 1 0 0 0 0 and 0. Okay, so yes, so if these are our two numbers, notice that when you have to make 1 as 0 in any number. Okay, if you want to make 1 as 0 in any number, you can notice that uh, to make this 1 as 0, it should overcome the power of 2, which is as big as this thing. Okay, so suppose anything is there, at one case it will be, suppose suppose at one case, by incrementing our our last some bits will be some of the last bits will be 1 1 1 1 1 1 this way. And when we increment 1, okay, when we increment 1, we will get 0 0 0, we will get 1 0 0 0, how many, 0 0. Okay, so what this tells is that if we have to make this 1 as 0, all the all the bits which are front of this 1 should also be 0. Okay, getting this point, right? If it is 1 by any chance in the x, if it is 1 by any chance, then it is not possible. Okay, because the property of binary number system is that when you overcome some power of a barrier of power of 2, the previous number of that is like 1 1 1. Okay, because 7 is having 1 1 1, 15 will be having 1 1 1, and when you come to 16 by 15, it will be 1 0 0 0. Okay, so that is the thing. So what it tells is that when you encounter 1 and 0, okay, you cannot have 1 and 1 in front of that. Okay, we have always we have covered this case 0 and 1. This is trivially there is no answer possible. Okay, but after 1 0, 0 0 is also trivial case, it doesn't mean anything to us. But if it is 1 comma 1, we are guaranteed to not get answer if it is after the 1 comma 0. Okay, so this is the key observation in this question. So finally what we have to do is that find an index, rightmost index. Okay, find an rightmost index which has its bits in n and x as 1 and 1. Okay, the rightmost index. Okay, so rightmost index. And what we have to do next is that after finding this index, and one more thing is that in our solution, suppose uh, what you can say is that suppose binary representation of n has 5 digits, suppose. So sorry for the disturbance. So one more thing is to notice is that suppose binary representation of n has 5 digits and binary representation of x has 4 digits, or suppose 3 digits, then it is a problem. Why I'll tell you. So let us consider this case. Let us consider binary representation of 10. So it will be 1010. Okay, and binary representation of what you say, suppose 6, so it will be 110. Okay, so so the size of this string is less than size of this string. Okay, so if I want to make 6 from 10, can I do it? So I cannot. Why? Because of that. Why? Because see, when I start incrementing this thing, okay, one thing is sure that I have to make this 1 as 0 here. Okay, to make this 1 as 0, I have to get 1000 on my list. Okay, on my list. Okay, so that is the thing. And when I get this thing on my list, all the other bits, all the other bits will get 0 because of this. Okay, so it is not possible. It is only possible in the case of the 0 that we will handle separately. Okay, when the x is 0. Okay, so that is the thing. So binary representation of n, size of binary representation of n should be string size of binary representation of x. Okay, so this is also a constraint. And finally, where were we? So we will calculate this index, uh, the rightmost index where the both bits are 1 comma 1. And what we can notice is that suppose we take two numbers, the previous two numbers only, 1101. What were they? 1 and 0, 110 and 1101, 10 000. So here that index will be this thing. Okay, this index where the rightmost index where the string n and x has 1, both are 1. So this will be that index. And what I can observe is that all the bits in the left of this index in the string n should be equal to that of the string x. Okay, uh, 0 comma 0 is trivially true, so 1 comma 1 is trivially also true. But if you want to convert 1 to 0 before this index, it is not possible. Okay, because this index have to become 0 as we have discussed. So that is the thing. So every index before that determined index should be identical in both n and x, not index but the characters on that index. Okay, so that is the thing. And every other thing we have to do in this right remaining right part. Okay, because left part is already sorted. And so if I want to convert this number to this number, what I have to do is that I have to make this bit, okay, next bit of this index as 1 and all other bits as 0. Okay, I have to do that because every other combination from this index after that index will be 0 comma 0 or 1 comma 0. Okay, only these two combinations are possible, because 1 comma 1 is not possible because already the determined index is the rightmost one, and 0 comma 1 is trivially not possible as it is our first case only. So these two cases are only remaining. Okay, so one more thing is that suppose I had numbers 1 1 0 1 1 1 1 1 0 and 1 1 0 1 1 0 0 0 0. So you will determine the rightmost index as this index, and you will see that this block satisfies our criteria. Okay, this criteria. And but you can see is that to make this bit as 0, you have to make the this bit in the subsequent number as 0. Okay, so to make this bit as 0, this bit as 0, you have to make the number above this to some level like 110 11. Okay, not 1 1 as also. So it will go all the way up to 1 0 0 0 0 0 0. So this will render these bits also as 0. Okay, so we don't want that. So we want at least one position. Okay, we want at least one position where both the bits are 0 comma 0 before the first combination 1 comma 0 comes. Okay, so I hope that is clear. And to get the minimum m required, so suppose this is a number 101. Okay, 00 00 10 10. So in this case, possible answers can be 101 1000 and 101 0100, as both the numbers satisfy our criteria for m, but we have to choose minimum m, so we will choose this number, second number. Okay, so I hope the solution is clear. So code is also pretty straightforward. So let us look at the code. So this is the thing. So these are just the helper function to calculate binary and binary representation of number and the decimal value of the binary string. So inputting taking input n and x. If both are equal, fine, just outputting n. If x is greater than n, then outputting -1 as already discussed. And if x is 0 and n is 0, trivially answer is 0, continuing to the further test case. And this is the part which regards to this thing, this thing. Okay, so it is also pretty straightforward to verify. And uh, don't forget to do this 1ll. Okay, so if you don't typecast this, it will cause integer overflow and your answer is going to be some wrong value, some garbage value. So don't forget to do this ll typecasting. Then if the size of both strings is not equal, outputting -1. This is to ensure one based indexing, a very cool way. And checking this trivial test case, no, oh, okay, trivial criteria where the n has 0 and x has 1, then our solution is not possible. And then fixing this index means the rightmost index where uh, both the characters at corresponding positions in both the strings is 1. So yes, and finally, what is this? So it is the check, for the previous bits. Suppose this is the index where you found the rightmost 1 comma 1 combination, and we have to check the all the bits in the left are same or not. Okay, that we also have to check. And this possible one bool is for that. And this is the check for binary this is the check for what I can say is that this thing. Mm, yes, this thing. So after 1 comma 1, there is consecutively 1 comma 0 also. In this case also answer is not possible. So this is that thing. And finally, just answer, declaring answer as binary of x and storing the index where we have to render that bit of answer as 1 and making all the other bits as 0 as done here. So rendering this bit as 1 and doing all the bits as 0. So this also is not needed because every bit in the x will be 0 only. So every bit in the x after that position, after this position, will be 0 only. And so that is the thing, toggling this bit as 1. And finally, 2 decimal, this helper function converts our string to the decimal number, and using this substring from 1 to answer dot size minus 1, going from 1 because we ensured 1 based indexing by adding this wildcard character t. So yes, finally outputting the answer in decimal. So yes, pretty interesting question. In my opinion, the best question of the bit manipulations I've ever seen. Uh, so yes, I hope you enjoyed solving this question and listening to the solution as well. Consider liking and staying subscribed to the channel. Thank you for watching the video. Thank you again. See you on the board again. Okay. Thank you.